A very good morning to all of you. So I cordially invite you for this engineering thermodynamics course. So today's classroom discussion topic is to discuss about the diesel cycle and air standard efficiency of the diesel cycle and mean effective pressure. So the motivation towards this particular topic is it is important to know how a diesel engine will work according to the diesel cycle. And what is the outcome of the today's lecture is you should be able to calculate air standard efficiency and mean effective pressure of the diesel cycle. So now let us see the diesel cycle. So it is basically introduced or invented by Rudolf Diesel, is the scientist in 1897. So he invented this diesel cycle. And in the previous class, we discussed about the Otto cycle. So that is the basic cycle for the petrol engines. And now here is the diesel cycle, that is all the diesel vehicles or the diesel engines will work on according to the diesel cycle. So this is also known as the constant pressure cycle, because the Otto cycle is known as constant volume cycle and here it is known as the constant pressure cycle. So what is the difference here is, so here the heat addition will take place according to constant pressure process in the diesel cycle, whereas in Otto cycle the heat addition is taking place according to constant volume process. That's why based upon the heat addition process, these are named as constant pressure or constant volume process. Now, how can we represent the diesel cycle on PV diagram as well as on the TS diagram? So here the 1 to 2. So 1 to 2, it is the compression process. So it is the isentropic compression process or the reversible adiabatic compression process. And here it is the only change you are able to observe from the Otto cycle. So in the 2 to 3 there we are having the constant volume process, but here you are able to see it is a constant pressure process. That is the heat addition is taking place in this particular 2 to 3. So that's why it is known as constant pressure cycle. So 3 to 4, it is once again isentropic expansion process, and 4 to 1, it is a constant volume heat rejection process. So now totally we are having the two isentropic process and one constant pressure and one constant volume is there in this diesel cycle. Now, as usual, here we have to derive the air standard efficiency of the diesel cycle and also the mean effective pressure. And we know that the efficiency formula is output by input. So in this case, work done by heat supplied. So you know that work done is nothing but heat supplied minus heat rejected. So heat supplied, that is the heat is supplied according to the constant pressure process. So MCP into T3 minus T2, that is the heat supplied, and heat rejected is taking place during the process 4 to 1 according to the constant value. So MCV into T4 minus T1. So when you deriving this particular the equation, so here you are able to introduce the another important parameter, that is cutoff ratio. So in the Otto cycle we introduced the compression ratio, that is R is equivalent to V1 by V2, but here so we are getting the another parameter in the diesel cycle, that is the cutoff ratio. So that is equivalent to V3 by V2. So what do you mean by the V3 by V2 means, just you see the, sorry, go to the previous one here. So here V1 by V2, that is the compression ratio, that is volume at the beginning of the compression stroke divided by volume at the end of the compression stroke. So that is the V1 by V2 is known as is the compression ratio. Now the cutoff ratio is, it is V3 by V2, that is where, because in the diesel engine, so that is where the fuel ignition, that is where the fuel is injected from that particular fuel injection nozzle, that is important one. So that is a fuel cutoff, that is cutoff is nothing but is a fuel cutoff, that is where the fuel injection will start and where the fuel injection will end. So this is the importance of the cutoff ratio. So the point 2 at which the fuel injection will starts from the fuel injection pump or the fuel injection nozzle, and similarly whenever it reaches to the point number 3, the fuel injection will stop. So that's why the cutoff ratio is basically dealing with the process 2 to 3. So compression ratio, because 1 to 2 is the compression stroke, so that's why it is a compression ratio. And here it is the heat addition is taking place according to the constant pressure process. So that's why here we are able to define the cutoff ratio in process 2 to 3 only. So that is the importance of the cutoff ratio V3 by V2. So whenever you are substituting all these things, so we are able to conclude that the diesel cycle efficiency is equivalent to is a 1 minus 1 by r to the power of gamma minus 1 into rho to the power of gamma minus 1 by gamma into rho minus 1. That is the important one. That is, so 1 minus 1 by r to the power of gamma minus 1. So it is the Otto cycle efficiency. So that is compared to the Otto cycle efficiency. So we are multiplying it by rho to the power of gamma minus 1 by gamma into rho minus 1. So that is the only thing, just we are multiplying to the Otto cycle efficiency. That is 1 minus 1 by r to the power of gamma minus 1. It is exactly similar to the Otto cycle efficiency multiplied with rho to the power of gamma minus 1 by gamma into rho minus 1, where rho is nothing but is a cutoff ratio and gamma is equivalent to adiabatic index and r is equivalent to is a cutoff ratio. That is very important one. So here also the compression ratio very important one. Normally in the diesel cycle we are going up to is a 24, 25, 26 compression ratios. And whenever we are also going beyond 24 and 25, the engine size will become very bulky. So to avoid that particular the oversize of the diesel engine, we are restricting the compression ratio up to only 24 in the modern diesel engines. Because whether it is the petrol engine or diesel engine, you can conclude one important point is that whenever the compression ratio increases, the efficiency of the Otto cycle also increases and efficiency of the diesel cycle also increases. So then why you are not increasing the compression ratio according to our will and wish? So that is why you are restricting the compression ratio only up to 12 in the modern petrol engines. So why can't we increase the compression ratio up to 20 or 30 in the petrol engines? Because as compression ratio increases, efficiency also increases. Then why you are not increasing the compression ratio according to our will and wish? So I already told you that in case of the petrol engines, the knocking is the main problem or the detonation is the main problem. So due to which we are restricting the compression ratio only up to 12. So similarly, in case of the diesel engine, so we are restricting the compression ratio only up to the 24 or 25, beyond which the engine size will become very bulky. So that is a basic reason, though the efficiency of the petrol and diesel engine increases with compression ratio. And how can we find out the mean effective pressure? Because the formula will remain same for the mean effective pressure. That is the work done divided by the stroke or the swept value. So we are able to get this equation number 13.8 for the mean effective pressure. So this is the final equation of the mean effective pressure. That is just it is only the work done divided by the stroke value, that is the V1 minus V2, that is the stroke or the swept value. Just you substitute here, you are able to get the mean effective pressure. So in the today's class, we are discussed about the working principle of the diesel cycle and how can you plot the diesel cycle on PV diagram as well as in the TS diagram, and similarly how can you derive the air standard efficiency and mean effective pressures of the diesel cycle. So in the next class, we'll solve some problems on the diesel cycle. I hope this particular class is very useful to you regarding the working principle and efficiency and mean effective pressure of the diesel cycle. So thank you one and all for listening this lecture on the diesel cycle. Thank you.